Hey, are we going to start?
Yes. Hi, everyone. Okay. Hi, everyone. Welcome to HPC AI Advisory Council session, this HPC AI track of SC Asia. So today, our workshop's major message is talking about next generation of the supercomputing architecture, which is cloud-native supercomputing architecture. So let's start the introduction for our expert from worldwide. So our first speaker is Gilad Shainer. Mr. Gilad Shainer is the chairman of HPC and AI Advisory Council. So he will give us the introduction for next generation data center, supercomputing center, and AI center architecture, which is the cloud-native supercomputing architecture. The following speaker is Professor D.K. Panda, who is from the American Ohio State University. He's a professor and university distinguished scholar of OSU. Then next speaker is Dr. Daqing Liu, who is from China JDEA Explorer Academy. He is a scientist of the JDEA Explorer Academy. So he has a PhD degree from Chinese University, USTC. So he will talk about their super deep learning system in JDEA Explorer Academy. Then following JDEA Explorer Academy's discussion, that's Professor Chen from Nanyang Technological University. He is associate professor of Nanyang Technological University. He is also the senior member of IEEE. He will also talk about the deep learning, his research job in the deep learning system. Then following speaker is Assaf Azrilevich. He is the senior director of NVIDIA networking team. So he's managing the NVIDIA rest of APAC solution architect team. So he will give a talk for the new data center become the computing unit. So then following Assaf, the speaker is Dr. Donglai Dai from the X-Scale Solutions. So X-Scale Solution is targeting the communication library optimization for the large-scale system. So Dr. Dong Lai, he is the chief engineer of X-Scale Solutions to introduce their latest work in the large-scale system. Then we have the James Legg from the University College London to introduce how to use BlueField DPU to optimize the applications. He's a PhD student of the University College London. Then we have some past HPCAI competition experience sharing. The first sharing is from the champion team of 2021 HPCAI competition. The team is the Southern University of Science and Technology. So Mr. Yiqi Zhang will give their experience sharing. The second experience sharing is from the second place of 2021 APAC HPC and AI competition. Mr. Ke Cai is a student from the Taiwan National Tsinghua University. The third sharing is also from the Taiwan National Chengkung University. He's also the second place of 2021 APAC HPC and AI competition, Mr. Sang Ling Huang. So during our speech, we will have Professor Tan Ting Wei Tan from NSCC Singapore and Mr. Gilad Shainer to close our 2021 HPCAI competition and announce our 2022 APAC HPC and AI competition. So this is our agenda for today's workshop. So if you have any questions, because time issue, we will not leave the Q&A time for each session. If you have any question after all of speech session, you can ask a question. Thank you. So now let's move to Mr. Gilad Shainer to give his talk. Thank you. Hi, Mr. Gilad.
Yeah, thank you very much, Qingchun, and happy afternoon, good afternoon, or late night, or good morning. Depends of where you are from. Let me share my presentation with you. There we go. It's great. So now we can see it here. So thanks again for Qingchun for the introduction of this afternoon session, and we will definitely include many interesting topics coming from different areas of supercomputing or high performance computing and AI. I wanted to talk about co-design architecture, which is key to not just enable next generation of platforms, but essentially to bring or enable architectures for future systems. Could be the large supercomputers, the Exascale platforms, large AI infrastructures, but also infrastructures which could be less of size. But we want to ensure that we maximize the effectiveness of the capabilities of each of those platforms. So first, a little bit about the council, a little bit about the HPC-AI Advisory Council. The council was established in 2008 with the main motivation to bridge the gap between technology and knowledge. There are great elements that are being developed, if those are hardware elements or software elements or platforms that combines both together. But there is a gap between what those technologies can do or can offer versus knowledge about how to use that. And that was the main reason behind the creation of the council, which today includes more than 430 member companies, universities or research centers all around the world, covering the main government centers and research centers and universities and leading commercial companies that create technologies and so forth. Those members contribute, donate from their time, from their capabilities, in order to form collaborations and enable or help to bridge the gap between technology capabilities and knowledge. The council is managing multiple activities under this mission, which includes managing cluster or steering cluster competitions that we'll announce later today, managing a compute center, a small compute center that includes multiple and different technologies, multiple systems with different technologies. So we can explore the fact of different compute elements, different network elements, different memory elements, different compilers, libraries, and so forth. And that combination give us the capabilities to analyze different kind of workloads, different kind of algorithms, and to understand how to optimize those. We do provide free access to the center, to the council members, so they can also do their own testing, their own investigation, their own development, and so forth. We have been publishing multiple best practices over the years, taking different kind of applications from different domains, different scientific domains, profiling them, testing them, understanding the impact of different hardware engines or different software elements on their performance and efficiency, and then publishing those results on the HPC Council, on the HPCAI Council website, so everyone can go and look on those, look what we did, what we explore, and learn from our conclusions to actually improve usage or performance of application running in other places. So when we look on the universe of scientific computing, made a small illustration of a supercomputing platform. Sometimes we're looking at a supercomputer just as a system itself, just as a supercomputer itself that includes the compute engines, the network engines that connects everything together, and local storage. But this is not the full universe. The full universe of scientific computing also include edge computing. And edge computing, those are, for example, the instruments that we use to do different kind of experiments, of scientific experiments. Those can be instruments that collect data from satellites and other places like that. And one of the important things moving forward is the ability to connect those edge devices, those HPC at the edge, the data collected from the instruments directly to the main system, the main supercomputer, in order to do a better analysis of information. We're also migrating compute to the edge in order to do the first analysis at the edge, in order to utilize different kind of technologies, including deep learning, to understand experiments and maybe tune experiments until we get the needed results, and then sending the right results into the supercomputing for further analysis. The system also includes external I/O elements where we can store more and more data that we collect. And everything here is essentially connected by the network. So the network plays a great role within the supercomputing or the supercomputer platform itself to take a collection of compute engines and make them work like a single engine. And it's critical for scale, but also the ability to connect the edge devices and external storage elements in a secure way, in a reliable way, all the way into the main system. So we will see in the future more emphasis on the edge, more emphasis on moving HPC to the edge to do analysis where we collect data, where we do our where our instrument sits when we do our experiments, and then send the data after doing a real-time analysis to a secondary analysis at the main system. In the past, when we built a traditional system, kind of the traditional data center or the HPC data center, we had a collection of compute engines, CPUs, accelerators, special hardware elements, storage platforms, and everything was connected by network that moved the data from one side to another side. The key things for the network were to drive high bandwidth and to do it in a very low latency, or to move data in a very low latency, to try and get the latency over the network as close as possible to the latency within a compute box, and therefore enabling CPUs, for example, or any other compute entities to work together and behave like a single compute entity. Now, as we looking on applications and trying to understand how we can build a better architecture, and what needs to be done in order to maybe change the traditional scope of data center architecture. We can look on profiling of different kind of applications, and there are cases of 4 applications here: VASP, the global forecast system, GROMACS, and GSI. And actually, what we looked is we profiled their networking aspect, and we profiled the compute time versus communication times. And you can see that first that a nice portion of the application is actually spent in the communication area, or in this case, a nice portion of the time spends in MPI. In VASP, around 35% of the application time is actually spent in communication cycles. GFS is almost 40%, GROMACS is 20%, and GSI is almost 70% of actually the time spends within communication frameworks. And since we in the traditional architecture, the CPUs, for example, were the only entity that did the compute and communications, so we're managing the communication cycles. We had to do compute and then communications and then compute and then communications, and therefore it becomes hard to try and accelerate performance or try to bring more entities that can work in parallel. And co-design, the idea of co-design started here, where the motivation behind that is to take an holistic view on the system and try to see where we should do what, and not necessarily doing everything on a CPU. For example, if we'll take MPI and move MPI to run on a different entity beside of the CPU, and do it in parallel. If you can achieve something like that, moving the work of the communication frameworks to run on a different entity, then we can reduce potentially 35% of the time of VASP, or 20% of GROMACS. So that means that we can improve the effectiveness of our supercomputing platforms, but actually spreading the different algorithms in different places. And then if you look on that, then one of the good ideas here is actually to maybe take MPI, maybe take communication work or the communication frameworks, and instead of doing that on the same CPU that runs the compute of the application, is to migrate MPI and run that on the network. Run that on the network adapters, run that on the network switches, and actually bring compute engines to the network. So to change the idea of the network just being something that moves data from one side to another side, maybe we can actually design a network that also do compute cycles in parallel of what the CPU is doing. And since if we do bring compute entities or compute engines to the network, we can run things much closer to the data. Doing MPI on the networks makes more sense, and that actually enables us to run the MPI, for example, in parallel of proceeding with the application computation cycles on a CPU. So that idea, that co-design idea, started the phase of bringing more computing engines into the network. And computing engines on the networks could be placed on the switched devices, can be placed on the NIC or the adapter, and those can be in forms of special hardware engines or programmable entities or programmable units which are part of the network. And with doing that, now you can actually process data as it moves within the network, which means that you can reduce time and improve application performance because of that. but also processing data on the network will reduce the data motion, will reduce the amount of data that actually needs to be transferred between servers or between servers and storage, which means that we can actually process more data. So it's a win-win-win situation by doing that. So one of the first elements as part of the code design that was developed together between commercial entity and a US research lab was to bring reduction operations to the network. Meaning, instead of doing reduce and all reduce and barrier, for example, on the server itself, to move those operations to be executed on the network. And in this case, the compute devices or the servers will need just to send data to the network, and the network actually will include hardware engines that can do the data arithmetics there or to do the data reduction operations. By moving data reduction operations, you can reduce the time of doing data reductions dramatically. On the left side, you can see running an example of running all reduce operation using recursive doubling, which is one of the options. And you can see all the iterations that are needed to be done across, in this case, 8 nodes in order to finish one reduction operations. On the other side, if we move the reduction activity or the responsibility of doing reduction operations to the network, in this case, we can actually do that in much less operations. And therefore, we're saving time. But it's not just saving time, but we're also reducing the bandwidth, the data, the amount of data that needs to be transferred by 2x. So half of the data that we need to send actually, and we can do it much faster, and we don't need to use the CPU for that. So we save CPU cycles. So that means that we can get, on one side, much lower latencies. And you can see some results on the left on a small scale and looking on performance of doing reductions on the software on the CPU or doing reduction, what's called sharp, which is doing that on the hardware. So it's not just that you get lower latency, but you actually get flat latency. You get flat latency regardless of the system size, and that's because the network is much more immune to the system size. The network is much more immune to the system scale. On the right side, you can see results of much larger system. Actually, those are results that were obtained on Toronto supercomputer. And comparing doing reduction operations on 1,500 nodes with 40 ppm. So you have 60,000 MPI ranks doing a reduction operation, and you can see the difference in time between running reductions on the CPU, which is software, or running that on the hardware on different message sizes. So there is a clear advantage here. Deterministic or latency, which is flat, half of the data motion, and of course, eliminating CPU cycles that were needed to do the reduction operations, and now we can do things in parallel. Another example for an engine that was developed as part of the co-design is doing tag matching on the network itself. So tag matching, MPI tag matching, requires essentially the CPU to be involved in any incoming MPI message. So every incoming MPI message will interrupt the CPU to do the matching between posted buffer, the tags on posted buffers, and the tags coming on the MPI message. And based on that match, to write the data into the right place. But the tag matching actually can be done on the network. So in this case, the network can get the list of posted buffers with tags, and the network can actually do the matching by itself. If there is a match, the network can actually do the full rendezvous protocol as well. Meaning, if it's large message, go to the other side and fetch the data and write it to the local buffer. And unexpected messages will actually need to go to the CPU, and that's essentially a bad flow. if you send an MPI message and you didn't prepare a buffer on the other side to receive that. But that's another example of a special engine that was created as part of the co-design idea of spreading algorithms on different active components within a data center. Programmable engines that we start seeing in new generations of networks, such as data processing units, for example, enable us to do even further than that. So there is collections of dedicated hardware engines to do different kind of activities, such as data reductions, tag matchings. There's new engines that are set to do all-to-all operations, for example, and so forth. But programmable computing on the network enable us to do more. Enable us to actually have processes now running on the network that can actually do data manipulations on host memories without the involvement of the host CPU. And that's by using RDMA. So RDMA enabled processes running on the network, on programmable engines on the network, to actually go and change data in different kind of host. Could be local or could be remote. And by doing that, we can actually move more algorithms. We can move algorithms that do not have dedicated hardware engines. We can move non-blocking operations. We can do MPI progress threads, for example, and so forth. Essentially moving a greater amount of MPI or other communication frameworks to be done on the network. To be done on the network in parallel of progressing the compute side of the applications on the host. It enables to bring computational storage. Ability to move checksums and compressions and other things and actually do that on the network. And of course, to enable user-defined algorithms to be migrated from the host and to run in parallel on the network much closer to the data. There are consortiums that actually develop the software elements to enable that. If those are libraries that's part of the UCF consortium, which include UCX or UCC, OpenSnappy, and so forth, it actually brings open source API or open source libraries to leverage the programmable computing within the network devices. I have a couple of examples, and Professor DK Panda is going to talk shortly after. And he's probably going to talk more about it, but this is an example of actually moving non-blocking MPI operations and run them on the programmable engines on the network. And by doing that, be able to run or run applications, on this case, running FFTs in parallel or using both the compute engines or the CPUs and using the network in parallel, and that enables actually to improve application or improve FFT performance by a nice margin. Another example, it's a recent work that was done by Georgia Tech and Sandia National Lab, which took a mini MD, mini molecular dynamic applications, and then moved part of algorithms of mini MD to run on data processing units, on programmable engines on the network, and by doing that, to get close to 20% performance improvement for applications. So those are examples of co-designs. The technology is being created, which includes the dedicated hardware engines and also include programmable engines on the network devices, which means that now it's becoming more of a software effort to take advantage of that. And that's part of the co-design. And we will see more examples of that moving forward. Just getting back to the console, last item here is I'm at the end of my time slot. We will continue and present more elements that are being created as part of the co-design. More activities around the software and how to take advantage of the new hardware capabilities that enables that enabled migrating different kind of algorithms from the server, the traditional will run on the server, to actually run on the network in parallel, and leveraging or building a more effective system, moving algorithms that makes more sense to run them on the network, to run them on the network instead of keeping them in a non-effective place. The council will host several conferences this year. The coming two are one in Switzerland, virtually in Switzerland, in March, and then another one's going to be virtually in the US, California time, in April. We do plan 2 or 3 more throughout the year, and potentially the second half of the year to actually go back to physical workshops, and as well managing the competitions, university competitions, where we enable students to actually leverage technologies in order to bring more knowledge to the universities themselves. So we will talk about the next APAC competitions. We're looking forward for the competition in June that will be part of ISC, and other elements. So with that, I'd like to thank you, and sorry that I took 1 more minute. Thank you very much for listening.
Thank you, Mr. Gilad. Thanks for your great introduction for the Exascale by code design architecture. Our next speaker is Professor Panda from Ohio State University. His speech is designing the high performance and scalable middleware for HPCAI and data science. Hi, Dr. Panda, please.
Yes. Yes, I'm sharing my slides. Are they visible?
Yes, we can see your slide.
Okay. Okay. Thank you. Good afternoon again for people in Singapore and all other time zones. Good night and good morning. It is a pleasure for me to be here to share some of the latest things, what we have been trying to do to design high performance and scalable middleware for not only just for HPC, but also for AI and data sciences. So as many of you know, we are in a very exciting phase. We are moving from petaflop to exaflop. The #1 system currently is the Fugaku system with 7.63 million cores. And of course, the world is waiting for exaflop systems to
Sorry,
come up.
Dr. Panda.
Yes.
Seems your presentation sharing has some problem. We can see your nose. So in the right side, can you change this, just duplicate the screen, or just because now we can see your next slide for your nose.
Oh, I see. Okay, okay. Let me see. Just give me, sorry for the.
Sure.
Can you see my screen?
Yes, we can see screen, but not in the presentation mode yet.
Yes.
Okay, no, it's okay. No,
Okay.
it's okay. Thank you.
Okay. So as I was talking, so the world is waiting for the exaflop systems to be coming up. Might be we'll see one of these systems in this year, 2022. So as you can see, the way the systems are coming up, and I think Gilad indicated to some of these in his talk, there is a lot of focus, not only just high performance computing, but also deep learning, machine learning, the AI workload, and also the data science workload. And we are in a very exciting world. In a sense, each of these subfield is actually trying to push the other one. Like once you have some good HPC systems, people are expecting more performance for AI workload and data science workload. And once people are successful, they're again demanding more and more HPC power. So the question is how we can design the software stack. And especially here in my group, we have been trying to focus on how MPI driven middleware can be actually designed and used for all these domains. And that too also not only on the on-premise system, but also on the cloud system. So in this context, I'll try to share, start with the MHAPIS project, which is the MPI project we have been doing for many years. And in that context, I'll also focus on how we can accelerate MPI application using DPUs. Gilad indicated to some of those. I'll go into more details. And then we'll also be talking about how you can accelerate deep learning, machine learning, and let's say data science applications with also Dask. So this is an overview of the MHAPIS project. If some of you are not familiar, we started this project almost day one of InfiniBand in almost like 22 years back. Prior to that, we were working on MiniNet and Quadrix. When InfiniBand came during October 2000, we were the very first one in the world to really jump in. And we had a open source MHAPIS version. That time it was MHAPIS 1, actually being demonstrated at Supercomputing 02. And then since then, we have been continuously working on, as you can see, this project is now 21 years old. And I'm very proud of my team. We are continuously making very sustained progress. And currently, this software stack is being used by more than 3,200 organizations in 89 countries. And just from our OSU website, we crossed like a 1.56 million downloads. And of course, it is a part of the Red Hat, SUSE, OpenHPC, SPAC. And also over the last 16 years, we have been enabling a lot of top 500 systems actually using our software as like a production quality software. So this is the overall architecture of our software stack. As you can see here, we take care of all different networking technology, not only InfiniBand, but IVAR, Procky, Omnipath, and Elastic Fabric Adapter. In fact, this week we'll be making a new release. You'll see 2 additional network support coming up for Slingshot and also the Rockport networks. So those will be coming out soon this week. And we also have support for like all different platforms, multi-core, many-core architectures. But this is where all our designs lies, the high performance and scalable communication runtime. And then we interface to the top level with different kinds of programming models, the MPI, PGAS, and hybrid MPI PGAS. And especially through MPI, we have been also able to link the AI environments and also the data science environment. So I'll be talking more on that as we go along. So we have the MHAPIS 2 broadly. There are multiple versions, but broadly we have 3 versions: the basic MHAPIS 2, the MHAPIS 2X, which is the advanced version, and MHAPIS 2 GDR, which is the more geared towards very much optimized for GPUs. So I'll try to go into a little bit of highlights of some of these designs and then performance numbers to show the way we are trying to design these software stacks. So here it shows the very latest MHAPIS 2 236, which is the latest version. This is trying to show on the very latest AMD Milan with InfiniBand SDR 200 gigabits per second. As you can see, we get very good impressive performance here. This is like a internode is around like a 1.8 microsecond. And within intranode, these are the latency around the 190 nanoseconds. And the bandwidth wise, here you can see within the node, we are able to go into like a 42 gigabytes per second. And then internode around 22.3 gigabytes per second for the SDR 200. Now, those are the point-to-point communication, but as Gilad indicated, like a lot of these MPI applications use collective operations. So we have been continuously trying to optimize. We have done a lot of point-to-point optimizations, but in these slides, what we are trying to show that we have also done a very tight integration and further optimizations together with the SARP. Gilad mentioned that is the in-network computing support. So here, if you will see these numbers, we have taken on TAC Frontera, that is one of the very largest system. As you can see, the number of nodes here are the time we took these experiments, it was very close to 8,000 nodes. And as you can see, this is like the T line is actually a software. And then here we have done the tight integration with the SARP. So this is for MPI already used with PPN1. And as you can see, we can give you almost like a 5x improvement as the message size increases up to 2 kilobytes. And as the message number of nodes increases, and here you can see that flat behavior, as Gilad was indicating, almost like here we see almost close to 8,000 nodes. This is an MPI barrier. We get benefits of like a factor of 9. And same thing also happens here, MPI reduce. Here you can see factor of 6, and much more detailed results are available. Actually, here we presented in the Exascale MPI workshop. You can take a look at that in detail. So here it's some sample numbers on the overall execution time. If you can optimize point to point, and if you can optimize collective, of course, you can see the benefits of the application. Here we are trying to take some numbers here. This is running on the EPFL system in Switzerland. And we are comparing with HP MPI and our MHAPS2X. And as you can see, this is running the EPFL mini application for neuron, neuroscience mini application, which is modeling the neuroscience behavior in our brain. And as you can see, compared to other MPI libraries, we can give you almost like a 36% improvement in this with our stack. So now let's go into this DPU offload. As Gilad was indicating. So the DPU, this is a generic architecture of the DPU. Bluefield 2 is being shown here. So we have a set of host processors, and now also we have a set of ARM cores together with the RDMA engines. So I call this like an executive and secretaries. So you can think of like these are the executive, the host processors, and these are the ARM cores are like secretaries. So just like in our normal day-to-day world, a lot of things you can offload to the secretaries. Executives actually offload so that they have more time to focus on their own task and decision making. The same thing we can try to do with respect to software stack. So in the beginning, we have started asking questions that can MPI functions be offloaded here? Okay, so MPI has a lot of different operations. So here especially, we have focused on non-blocking collective. So just to give you a little bit of quick overview, if you are not familiar, in the earlier standards of MPI, prior to MPI 3, it used to be all blocking collectives. That means if I do all the processors will initiate all-to-all and then will wait there until the operation finishes. Okay, so then what is happening is, of course, all-to-all may involve a lot of exchange of communications, and the process can do those, but they are not doing any computation. But then the MPI 3 standard actually introduced the non-blocking collectives. That means we can do the computation and then initiate the non-blocking all-to-all. But while the all-to-all is happening in the system, the computation can also proceed. Then we can actually get overlap of computation and communication, and that will lead us to real benefits at the applications. But of course, the challenges have been there that when this non-blocking communication happens, who actually handles the communication? There have been a lot of solutions in the literature with respect to like host-based or some additional threads. But then when you are using all the cores of the system, you actually don't get that much overlap. So this is where actually the new DPU architecture gives a newer opening to see whether we can actually take advantage of that. So we have actually been working on this project for almost now 1 year. In fact, we have a complete solution. We call it MHAPS2 DPU. This is being done jointly with X-Scale Solutions. You'll actually hear a talk from X-Scale Solutions a little bit later on today in this program. So we made actually the new release of this our package just 2 weeks back. This is based on MHAPS2 236, and it has support for non-blocking all-to-all, all-gather, and broadcast. I'll go into some more detailed results. We have a newer release coming up, might be in another week, that will actually try to push even the performance benefits higher. So here, let me try to start with some initial numbers. So this is like a OSU I all-to-all. That means that is the part of the OSU micro benchmarks. Many of you might be familiar. So we are just reporting numbers from there. So as you can see here, first we are trying to understand the overlap capabilities. And this is what I indicated, like let's say the host processor like executives are trying to do the computation, and then the ARM processors are trying to do the offload. Can we really have overlap capabilities? And as you can see here, the red lines are like red bars are the basic MHAPS2 design. So these are for the eager message range. Since you use copy and all, you get very little overlap. And also the rendezvous, because you send RTS, CTS, you don't get overlap either. But now if you see the MHAPS2 DPU, these numbers are very close to 100%. So that means we can truly actually offload this non-blocking all-to-all to the DPUs. So now let's try to see, that is like just the overlap, but what is the impact on the overall time? So here the overall time we are measuring compute plus communication because that is the behavior we want. That means we initiate the communication and then do the computation. And if it can be overlapped, we'll see the benefit. And that's what exactly is shown here. These are numbers are 32 node 16 ppn, like a 512 process runs. And you can see you get almost like a 22% benefits in the overall execution time of this pattern, where you have communication followed by computation. And on the right hand side, this is a 1000 process run. And here you can see again 21% to 27% benefit here. And the same trend that was for a larger system, even for a smaller system like a 16 nodes, we see very similar things. Here 256 process runs, we get around 18% benefits. Here another 256 process runs, we are getting 20%. So as you can see, it is the same hardware. Okay, now the question is how effectively we can try to utilize the processors in this hardware so that we get this kind of benefit. So here actually this is like a not just the I want to highlight here. So this is not just the micro benchmarks we showed earlier, but these are the actually P3D FFT numbers. So we actually worked with this is an application. The FFT is very dense communication. We worked with the developers of the P3D FFT from San Diego Supercomputing Center, and they actually rearranged the code to have non-blocking all-to-all with computation, and we are seeing the numbers here. And this is also the similar P3D FFT. We're trying to scale it to 32 nodes. Here you can see 1000 process runs, and we are getting like 18% to 21% benefits in the overall execution time. And even for like a 512, similar kind of things we are seeing here. Now we have gradually now expanded to other collectives. So this is OSU All Gather. That is also very frequently used collectives. And here you can see even we get up to like a 41% improvement, 48% improvement. And these improvements change based on the message size, the PPN, system size. We are continuously trying to optimize these and tune it for different kinds of platforms. And this is the IBcast, that is non-blocking broadcast, the same kind of trend you see. Here, in fact, like with the 32 node 16 ppn, you see almost 48% improvement. Okay. So this is another example, like the iScatter. This is currently not available. It will be available with the upcoming release. The same story, we get almost like a 52%, 49%, 64% improvement. So that means we have a very good solution here to really optimize or offload non-blocking collectives. Now, of course, the question is how we can take that into the application. So here we are actually looking for a lot of collaboration. If you people have applications where you can actually have some of these non-blocking collectives, or if you have blocking collectives but you are willing to modify those, so please feel free to contact me, and we'll be very happy to work with you and then try to see how we can deliver the best kind of performance for your end applications. So that is kind of the DPU. Let me switch the gear a little bit. GPU has been there for many years, and in fact, almost 10 years back, we worked together with Mellanox and NVIDIA at that time to have this. When the GPU direct RDMA technology came, we were the very first one again to bring that to the MPI layer. Okay, and now of course all other MPI layers libraries are using the GPU direct RDMA. But if you take a look at this number, you see 1.85 microsecond. We are able to actually send data from a GPU of one node to the GPU of another node, not on the same node, in just 1.85 microsecond. And that gives a very big benefit with respect to latency. We can actually push bandwidth and bidirectional bandwidth, and those lead to real benefits in the application performance. So that is with the NVIDIA GPUs. Our latest release actually also supports for the AMD GPUs. We see very similar trend. Here you can see, like here we are comparing our latest MRAPIS to GDR release with OpenMPI release. Here you can see like from the AMD, the GPU of one node to the other node, we can do it like a 1.75 microsecond. And if you take a look at collectives like a Bcast or all reduce, we give very significant performance benefit compared to even to here with the OpenMPI. Now, for the last year, we have been moving into one more step. It's trying to bring even on-the-fly compression. So this is a very newer mechanism. Now you see that a modern GPUs like a V100 or A100 has a lot of cores. So of course, people are trying to utilize that for mostly computation, and sometimes for communication like collectives and all, you try to optimize. But we are trying to push the boundary a little bit further, because especially if you are trying to send large amount of data, can we actually compress and then send it? And this we need to do on the fly. Okay, so we had a paper here. I'm trying to show some numbers from the IPDPS earlier last year, and here you can see, and these are like a lossless compression. So we have all the different kind of compression schemes. Here we are trying to show AWP ODC. This is a seismic simulation application, and as you can see, we are able to deliver the correctness for the entire execution with on-the-fly compression, and we are able to push the performance. Here almost like 18%. This is the total flops. The higher is better, and then the right hand side is the overall execution time. We are able to reduce 15%, 26%. So these are some of the basic HPC side. So let me move into the machine learning and deep learning side. So what we have done, many of you might be familiar with this hoverboard, torch distributed, deep speed. These are the newer frameworks which are coming for the deep learning. So what we have done a very tight integration of these frameworks with our MPI libraries. So this is what we call it like MPI driven approach, because MPI libraries like our MAPIS2, as I showed earlier, has very good optimized support for all the collectives, and many of these deep learning frameworks actually use collectives, like already use all-to-all, so they can directly take advantage of it. And in fact, we have this project called HiDL, High Performance Deep Learning. So you should be able to directly download our libraries and build it yourself, and then you will see real benefits. All the end applications can run transparently without any issue and get good performance. So in this context, let me try to show you some initial results. I'll try to focus on out of code training. I'll show an example of like a digital pathology, and also we have a very tight integration even with the machine learning applications. So here it is some numbers. This purely CPU based deep learning. These numbers are taken on the TAC Frontera system. And as you can see, we are able to scale very nicely with our MAPIS2X library with here the ResNet 50. As you can see, using 2000 node, we can actually really do the training in just 7 minutes here using even the pure CPU. With GPUs also, we see the similar kind of a trend. These are taken on the Livermore Larsen system with the 256 voltage GPU. And as you can see here, we are comparing our MAPIS2 driven solutions with the nickel based solution. Nickel is also a collective communication library. And as you can see, since MPI is very much optimized, we are able to actually give you even higher performance here, almost 10,000 images per second faster using the MPI driven approach. Now those are with basic data parallelism, but gradually, as you can see, the model sizes are increasing, and you cannot fit those within a single GPU. So as you can see here, depending on the different GPU and CPU memory, so these are the regions where only model parallelism is possible. Okay, so we have actually developed here this HiPAR framework. We presented this at IAC 2020, and this is, you can see, this is a CPU-based system like on the Frontera. This is a ResNet 1001, and as you can see, like on a 512 nodes, we are able to go almost like a speed up of 481x. Okay, we are able to using the model parallelism and getting very good efficiency also, scaling efficiency for these. So then after that, we have extended this to newer kind of frameworks, the model parallelism. So this is the result from the supercomputing 20. So here you can say like we have this framework called James, and we are able to scale it to 1000 GPUs on the Livermore Larsen system with a very good efficiency. As you can see, we are able to get like a 97% efficiency here. So then we are gradually moved. This is the transformer models. So here we have used a new approach called subgraph parallelism. So as you can see, like this kind of a DNN architecture, there are so many different graphs. So how you can actually, given a set of GPUs, how do you do the perfect partitioning here to get the best performance? So this we presented at also the IPDPS 2021. And here you can see, using our approach, we are able to up to 1000 GPUs. We are able to get almost factor of 3 improvement compared to the data parallelism. Okay, so these solutions actually show that now using model parallelism and hybrid parallelism, you will be able to actually accelerate your deep learning training time. So for a concrete example, here we have been working at the Ohio State University together with our pathology colleagues. So if some of you remember, like when we go to the doctors, they have the pathology images, but these are very large images. They call it like a whole slide images. They cannot fit it into a single GPU. So they were trying to do some tiling and trying to do learning with the GPUs. In fact, with one GPU, it was taking almost 32 hours. With 4 GPUs, we worked with them to reduce to 7.25 hours. Then gradually we improved. Even finally, with 128 GPUs, we were able to reduce the time to 0.46 hours. The entire training kind of things with a set of WSI images, and we were able to give almost like a factor of 22x improvement here. So those are the kind of the basic deep learning. We are following a similar trend for the machine learning. So what we have done here is I talked about this MVAPs to GDR library, and we have linked it actually with the MPI for Pi package so that all your QML applications can actually run with the MPI layer. So we released this last year. We have a new release coming up, might be next month. We'll be releasing it. And then if you take a look at here, we are comparing with the nickel. This was the last year's paper, MVAPs to GDR with the nickel version available at that time. And as you can see, we are able to give speed ups almost like a factor of 1.6, 1.4, 1.4 kind of things. These are the very common machine learning algorithms, and we are able to push the performance. So similar to the high performance deep learning and machine learning, we are also taking a look at the data science applications. So those are the newer generation applications which are coming. And here especially we have been focusing on DAST, that is getting a lot of popularity. And similar to QML, we have also done we have done a very tight integration through this MPI for Pi package with MPI for DAST. Okay, so now you can see that now this entire DAC ecosystem can just run with the basic MPI. You don't need any other libraries. And of course, the DASC ecosystem has the support for TCP and UCX. So we made this release March of last year, and again, a new release will be coming out this year. This has support for both CPU-based as well as GPU-based DASC-oriented operations. And let's take a look at the performance gains. So here you will see that we are comparing. These are all running on the IB networks. So the basic DASC has the IP over IB support or UCX support, but now if you see the MPI for DASC support, these are the execution time. So the lower it's better. We are able to give you almost benefits of 3.47x here, almost 6.9x here. And this is like a 2.9 and 2.9. So depending on different workloads, these MPI driven solutions are able to actually give you far more benefits because MPI library has always been optimized with a lot of this communication, and we are able to take advantage of that for the data science applications also. So now you can actually combine some of these things. So I talked about the compression earlier, on the fly compression here, that was purely for HPC, but that also can be applied here. In this case, for the DASC application, we see similar kind of trends here. As the number of workers increases, here you can see on the DASC, we are able to get almost like a 1.56 improvement in terms of the throughput and 37% reduction in the execution time. So with this, let me conclude. I'm almost finishing here with the time. So if you take a look at the bigger picture, I mean, all these upcoming Exascale systems and cloud need to be designed with a holistic view of the HPC, deep learning, machine learning, and data science. And this is exactly what we are trying to aim in our group. I presented an overview of some of the opportunities and challenges in designing the software stack for these systems, and also presented a set of solutions where the applications can actually take advantage of the very latest cutting edge technologies to really boost their performance. And through these, we are aiming for to go into the next phase of the systems like the Exascale systems and the Jetascale systems. Will be able to get very good performance. So with this, let me thank all our sponsors here, and also last but not the least, these are all my heroes. These are all the students and staff from the group who have worked over the years. So every time I give a talk, I plan to give a real credits to all of them. Without their contributions, these would not have been possible. While we have been doing a lot of good work continuously, I'm looking for very bright and enthusiastic personnel to join my group. So if you are listening to the talk and then you'd like to come and work in our group as either as a PhD student or postdoc researcher, MPI or big data programmer or deep learning programmer, please send me a note. So with this, let me conclude here. If there are any quick questions and if we have time, I'll be happy to answer. Otherwise, please send me your questions in this address and I'll be very happy to answer it. Thank you.
Thank you, Professor Panda. It's amazing to through the middleware optimization can get so much performance enhancement for HPCAI and data science. Thank you again, Dr. Panda. Our next speaker is Dr. Daqing Liu from China Jingdong JD Explorer Academy. His speech is JDEA Super Deep Learning. So please, Dr. Liu.
Hello everyone, I'm Daqing Liu, a research scientist from JD Explorer Academy. Today I'm going to introduce several recent works on super deep learning from academia. Here is the outline. Towards to super deep learning, I will first review the evolution, including trade data and computation. After that, I will introduce the theoretical foundations, universal approximation. After that, I will present the architectural design based on our recent work VITAE published on Neuropus. Finally, I will introduce a new generation paradigm with our TWFA network. First, the evolution of super deep learning. Taking the Alan Turing test as the birth point of AI. AI has grown through several waves since its birth to now. The first wave, which we will call the program intelligence, AI systems mainly conduct several programmed tasks, and its mainly form was an expert system. The expert system transforms the information input by human into logical experience in the machine, and reason the results by symbolic algorithms. The second wave is known as the perceptual intelligence. Machine learn to hear, think, and recognize objects. In the second wave come BP neural networks, which achieve very good results in simple pattern recognition tasks. However, as the size of the data gradually become larger, its bottleneck gradually manifests, leading to the arrival of the third wave of artificial intelligence. The third wave is the development of cognitive intelligence brought by the rise of deep learning technology. The so-called cognitive intelligence is that the machine can not only think, but also have its own reasoning ability, where it is causal reasoning or understanding of natural language, especially now we see that GPT-3, a large-scale neural network, can create some compositions by itself. In this way, it has some ability to understand language, which means that the machine has learned some cognitive abilities. The first three waves of AI were what made AI already capable of large-scale applications, but it was of limited quality. Recent years, we have seen a boom in super deep learning, where deep learning models used to be small, maybe a few megabytes or 10 of megabytes in size. By now, GPT-3 such models have parameters of 170 billion. In the era of classical machine learning, the bigger models are easy to outfit, and the generalization is very poor. But in the era of super deep learning, when the model is big enough and the data is big enough, the generalization is getting better and better. In such a super deep learning paradigm, do many traditional machine learning and deep theories need to be updated? This question from the research direction of academic super deep learning. So, why super deep learning will be the future trend? First, from the perspective of data volume, we are in the era of massive data with near exponential growth in the data size. Massive data and supercomputer computing power has also evolved to support the computation of very large models. We have reached the level of the explosion of super deep learning. In order to adapt to the data scale, the deep learning model size also shows a corresponding growth trend. To this end, our academy entered into a strategic cooperation with NVIDIA to jointly build the industry-leading superpod cluster. The supercomputing cluster of JDEA adopts the standard superpod architecture, consisting of 114 DGX A100 servers with S+1 infinity band between servers to achieve high-speed interaction between servers. And the cluster is also equipped with separate DNA high-performance storage servers to achieve optimal performance of the cluster from three aspects: computing, communication, and storage. The cluster will support the main research directions of JDEA super deep learning. Our strategic cooperation includes the following areas: large-scale training, large model inference, AutoML platform, resources optimization, talent training, and co-marketing. Next, I will briefly talk about the theoretical foundations of super deep learning. The universal approximation means neural network can approximate any continuous functions. This theory had been proved in 1989. Specifically, if the network is infinity wide, the multi-layer perceptron has universal approximation ability. After that, in 1993, it was proved that even multi-layer networks can approximate any continuous functions if the network is infinitely wide. Till 2017. It was proven that finitely wide networks can also have universal approximation ability. Time comes to 2020. We have new findings that deep neural networks can also approximate any distribution. The universal approximation suggests the meaningful of very large models, for example, super deep learning models. But why do we have confidence in super deep learning models? What about established theoretical guarantees? Recently, we have a preliminary demonstration of the superiority of the super deep learning model in terms of generalization theory. First is the first equation deeps the generalization ability of the pre-trained model. When the amount of trained data NPT used by the pre-trained model is larger, then the upper bound of the generalization error of the final pre-trained model is smaller, which means that the generalization ability of the pre-trained model is stronger. Then we look at the second equation, which describes the generalization ability of the model after fine-tuning. The formula shows that the upper bound of generalization error of the model after fine-tuning is limited, and the generalization ability of the model is guaranteed. Together, those two formulas show that super deep learning models can help AI perform downstream tasks better. The very large-scale datasets employed in the pre-trained stage help obtain high-quality models. Minimizing the domain dependency helps the fine-tuned models generate better on the target domain. Although the underlying theory is still lacking, to some extent, we have made preliminary arguments for the value of super deep learning. Thus, the super deep learning studied by our academy is composed of mega model, supercomputing cluster, and massive data. Let's first look at the architectural design of super deep learning. In 1998, Qingchun presented the earliest CNN named LeNet-5. The convolution neural networks introduce inductive bias of local correlation, making it training efficient. After that, the residual connection makes the neural network can be very deep and is the training of substantially deeper networks. Here is the question: what is next beyond CNN? The answer is vision transformers, which have experienced rapid development and show promising performance in many vision tasks, including classification, detection, segmentation, pulse estimation, and so on. Classic vision transformer first embeds image into several tokens and then use several transformer blocks to extract features. However, the vanilla vision transformer are training difficult. The reason located on the inductive bias in CNN, including local correlation and scale invariance. The local correlation means spatially just pixels and correlated. The scale variance means objects of the same class are always in different scales. Even though transformers have shown a promising performance in vision tasks by embedding images into sequence, such a pipeline doesn't take images properties into consideration and needs to learn such inductive bias through large-scale training data and a longer training schedule. Such requirement is not affordable for researchers with limited computational resources, as well as is not friendly to the protection of the environment. Is there a method for us to elevate such data-hungry issue? To be specific, can we improve vision transformers' performance by introducing the required inductive bias into them? Many trials have been made in this direction. There are many two kinds of methods to introduce inductive bias. The first kind of method is to implicitly introduce inductive bias into transformers with techniques like distillation. The representative method is DIT. It employs another CNN network as teacher to distill the inductive bias into transformers. Another distillation token is employed and used to calculate the loss with the teacher's output. In this way, the transformer model implicitly learns the inductive bias. The other kind of methods choose explicitly introduce inductive bias into transformers by using convolution in transformers. For example, CEIT inserts convolution into the feedforward network to introduce locality into transformers. However, they don't take scale invariance into consideration, which is an important inductive bias in classification, detection, segmentation, and so on. By the way, the simply adopt the sequential concatenation of the convolution and transformers, which does not consider the possibility that transformer and convolution may be complementary to each other. Such complementary is expected as the transformer is good at modeling long-range dependency, while convolution is Gilad modeling short-range dependency. Here we propose the VITAE model to introduce two kinds of inductive bias into transformers and to improve the convergence and the performance of vision transformers. The main contributions are twofold. One, the ultra-low convolution layers of different dilation rates for modeling scale variance, and two, a parallel convolution branch for modeling locality. There are two kinds of cells in the proposed VITAE model, namely reduction cell for downsampling, which contains the ultra convolution layers and the parallel convolution branch, and the second normal cell, which contains the convolution branch in parallel to the transformer layer. In the reduction cell, pyramid reduction module is adopted. The pyramid reduction module contains several dilated convolutions and is responsible to reduce the features' spatial size and capture different scale features. The generated feature will then be preceded by a multi-head transformer module to model long-range dependency. Besides, a parallel convolution module is adopted to model short-range dependency with three multiple convolution layers. Another feed-forward network is then adopted to conduct feature fusion and projection, with the joint working of pyramid reduction module, parallel convolution module, and attention module. The reduction cell jointly embed locality, multi-scale information, and long-range dependency into the extracted feature. The normal cell is almost the same with the reduction cell, except that it does not contain the pyramid reduction module, and there is no spatial size change occurred in normal cells. We stack the reduction cells and normal cells to formulate the final VITAE model. We adopt two different stacking policies. The first one follows the classic setting of vision transformers. We first use three consecutive reduction cells to embed the feature to 1/16 of the image size. Then the embedded feature is concatenated with a random class token and processed by several normal cells. The final prediction is got through the class token. The second setting is set-wise structure, which is beneficial to the application of VITAE models in downstream tasks. We struggled to arrange the reduction cells and normal cells. The final prediction is got through the average pooling of all the tokens as there is no class token in the set-wise design. To investigate the efficiency of the proposed inductive bias in vision transformers, we test the different settings of reduction cells and normal cells, including different settings of dilation rates, whether use parallel convolution module in reduction cells, and how to fuse the feature from multi-head self-attention and parallel convolution modules in normal cells. Generally, with the explicitly introduced inductive bias, the vision transformer module achieves better performance, which demonstrates the efficiency of explicitly introduced inductive bias into vision transformers. We studied the data efficiency of the proposed VITAE model. We separately trained the DIT to T2TVIT and the VITAE model with 20%, 16%, and all the training data from ImageNet for 100 epochs, as shown in the left part of the image. VIT model can be better deal with the data shortage problem. Then, we studied the training efficiency of the proposed VIT model by training for 100, 200, and 300 epochs with all-train data from ImageNet. It can be observed that VIT model trained for 100 epochs beats the T2T VIT and DERT trained for 300 epochs. It can be concluded that VIT is much more data and training efficiency with explicitly introduced inductive bias. Here is the performance on ImageNet top 1 accuracy. It can be concluded that VIT model achieves the best performance on the restriction of different model size, no matter using the classic design or stack-wise design. Besides, the static-wise design of VIT model generally works well than the classic static VIT models. Here are the visualization and performance comparison on downstream tasks, including object detection on MSCOCO, semantic segmentation on ADE20K, video object segmentation on VOS Davis 2016 and 17, and human pulse estimation on PulseCoco. The results demonstrate the performance gain of VIT also preserves in the downstream tasks with less parameters. We also visualize the feature of the proposed VIT model and classic transformer model T2T VIT. It can be viewed that the feature extracted by VIT is more concentrated on the target objects in the image. No matter the size of target object is larger or small. Besides, the feature generated by VIT contains less noise compared with T2T VIT, as it pays less attention to the background region. In conclusion, in this paper, we explore the issue of large-scale data and long training schedule in vision transformers, and try to address this issue by introducing inductive bias into vision transformers. Extensive experimental results demonstrate that the new architecture significantly improves the vision transformers coverages and performance, and outperforms representative vision transformers in various aspects, including classification, detection, and segmentation. In the next section, I will introduce a new generation paradigm of super deep learning. Recent years, a number of CNN-based generative models have been proposed and achieved significant progress on conditional or unconditional image generation tasks. Until now, CNN-based generative models are good at synthesizing high-resolution and high-fidelity object images, which include but are not limited to flowers, human face, and buildings. However, generating complex real-world scenes with include multiple instances with variant layout and scale has still been a challenging task. To its difficulty of synthesizing complex things, previous works usually breaking the task into several steps. For example, layer-to-image models these tasks as object generation than image generation pipeline. Each object is controlled by a certain category code and an uncertain appearance code. For better controllability, loss scans first generate the semantic masks from layers. Overall, CNN-based layer-to-image generation methods have achieved promising performance on textual generation. However, they may still suffer from accurately modeling the dependencies among pixels, which hinders the model generated more realistic scene images. The transformer architectures that model interactions between input tokens with solid attention mechanism have demonstrated great potential on both language and vision tasks. Recently, works further explore the potential of transformers on conditional visual content generation. First, VQGAN is trained to compress image into finite discrete representations of tokens. Then, an autoregressive transformer is trained to model the dependency between discrete image tokens. Through modeling together with conditional signals, such as text, class tables, and key points, transformer demonstrates the strong capability of generating semantic controllable images. However, the entangled modeling on patch level and pixel level CNN-based methods, or object level and patch level transformer-based methods, prevents the model from capturing inherent instance structures, leading to blurry or cropped objects, and increase the burden on the future learning because the model must learn the two levels information similarities with only a few images. The overall of the proposed transformer with focal attention TWFA framework for the layout-to-image task, given a layout and an image as input, we first tokenize them into sequential discrete object or patch tokens by the embedding encoder. Next, predict the next patch tokens by the TWFA, and then during inference, generate the RGB image from all predicted patch tokens by the decoder. The image illustrates the of different attention mechanism with connectivity metrics. A is vanilla attention follows a causal mask, neglecting different interactions. B is object-to-object interaction enhance the modeling of object-level relationships. C is object-patch interaction, makes the patches to realize the object categories. D is patch interaction, introduce the composition or behavior of layouts. And E is our focal attention. It captures both object-level relationships and patch-level structures. To validate the effectiveness of the proposed TWFA, we compared our model with both scene-based and transformer-based complex scene generation methods. The quantitative results by the involved computers on both Coco Staff and visual genome datasets are reported in table. Compared to them, the proposed TWFA achieved significant improvement on all metrics. Here, we provide several visual comparisons of the complex scene images generated by our methods. According to the visual comparison, we can observe that previous methods are capable of the generating reasonable texture and patches. According to the generated texture, we can roughly understand the synthesis scene. However, they failed to accurately model the instance structures. For example, the zebra generated by loss scan looks like a collection of the animal form. According to the visual examples, the proposed TWFA performs better on constructing relationships between objects and modeling structure of an instance. As shown in the table, all experiments on field shot show the superiority of our methods. Meanwhile, accompanied with the increasing of short number, better generalization performance can be achieved. In the image, in the figure, a new class with 25 samples was employed to fine-tune our TWFA. From the visual examples, we can also see our TWFA show better instance structures. Here is the conclusion. In this talk, I introduced JDEA super deep learning from the evolution, theoretical foundations, architectural design, and generation paradigm. That's all. Thanks.
Thank you, Dr. Liu. Our next speaker is Professor Chen from NTU. His speech is deep learning is shaping the future of content creation. So, Professor Loy, please.
Thanks, Qingchun, for the introduction. Okay, so I'm Kevin from NTU, School of Computer Science and Engineering. I'm also the director of MM Lab at NTU and co-associate director of ASLab. So just now, Dr. Liu has shown many examples of generating images by using deep learning algorithms. Now, as we may all know, AI is increasingly used for content creation, for instance, to generate text, video, music, and images. In this talk, I will focus on visual content creation, particularly on images and videos. So a lot of content that we consume every day uses images to convey emotions and tell stories, to show us basically stories and products. So images and videos are thus a very interesting class of content that are being artificially generated with the AI algorithms. So in the past, visual contents are generated solely by human, either through drawing, taking photos, or manipulating through using art tools like Photoshop. So with the images of deep learning techniques, AI can now be used to automate many mundane, repetitive tasks involved in producing visual content. So for example, one can enhance details easily by using AI. So you can add pixels to a low resolution image easily. So I will show some examples later. And you can edit content of existing images of videos, for example, by removing unwanted objects from a video. Or you can create a totally new content by pairing with, for example, with specific styles of your interest. And the good thing is that I can do this extremely fast at high volume with high production quality. So all these recent advancements are originated from a work published in 2014 by Ian Goodfellow. So the network is called Generative Adversarial Networks, or GANs for short. So it is an approach to generative modeling using deep learning methods, such as convolutional neural networks. The generative modeling is an unsupervised learning task in machine learning that involves automatically discovering and learning the regularities or patterns in input data in such a way that the model can be used to generate or output new examples that possibly could have been drawn from the original data set. So to train a generative model, we first collect a large amount of data in some domain. So if you want to generate like images, then you need to collect millions of images to train the model to generate the daylight. Quickly go through some details of GAN in case you are not familiarized with it. So GANs are a clever way of training a generative model by framing the problem as a supervised learning task with two submodules. So there's a generator model and that's a discriminative model. So the generative model that we train is to generate new examples. And the discriminative network over here tries to classify the examples either as real, which is from the real domain, or fake, that's being generated by the generative network. So these two models are trained together in a so-called zero-sum game or adversarial game until the discriminative model is full about half of the time, meaning that the generative model is generating plausible examples. So the images shown here, of course, is not at good quality, but with recent techniques, then we can perform much better than the original network proposed back in 2014. So GAN is now becoming a very exciting and rapidly changing field, delivering on the promise of the generative models in their ability to generate realistic examples across a wide range of problem domains. So most notably in the image-to-image translation task, so one can generate a photo or translate photos from day to night, from winter to summer, and many more. And one also can generate photorealistic photos of faces, objects, scenes that even human cannot tell whether they are fake or genuine. And in the domain of image restoration, so one can use Gantt to the problem of image super resolution to fill in the missing details in low resolution images. So there are many exciting applications out there. So this is another example by NVIDIA. It's called Gargantua. The user can just input a very simple segmentation map, which is a sketch, very simple label sketches that depict the layout of a scenes. Then with just a button, you can generate a very realistic image that looks like this. And this is another very cool example. It's called DALL-E, which is a 12 billion parameter version of GPT-3, okay, trained to generate images from text description. So basically, you just need to give a text prompt like this. For example, an illustration of a baby dark and reddish in a tutu walking a dog. Then the model can generate a very nice looking, very realistic images like this. And this is another example. Yeah, an armchair in the shape of an avocado. So you can generate this kind of images with very nice, very high quality. So researchers just found that this kind of model has diverse set of capabilities, creating anthropomorphized versions of animals and objects, and combining unrelated concepts in plausible ways. So this is all impossible in the past few years, before the emergence of GAN. So in our lab, we're also doing a lot of work in content creation and editing. So our lab is formed back in 2018 with the research focus on computer vision and deep learning. So it's now a group with 3 faculty members and more than 40 members, including research fellows, research assistants, and PhD students. So our lab members mainly conduct research in super resolution, image and video understanding, content editing, and generation. So next I will show what we have been doing in content creation and content editing. So the very important focus of our group is content enhancement. So we mainly focus on image and video super resolution. So you have seen this over and over again in many Hollywood movies, whereby, let me play this video. So this video is extracted from the movie Jason Bourne. So the ex-CIA officers, we tried to escape from the current CIA officers. Yeah, but with the technologies of super resolution, so the CIA can get the face of the person from the poorest video quality. Okay, but just like getting an enhanced version of the blur videos. So is this possible? Yeah, turning a blurry and low resolution image to an enhanced image. So this has been a very difficult problem in the past. So in the past, people have been solving it for the past 35 years because of the problem of unknown degradations. It has one-to-many solutions. It's a U-post-inverse problem, meaning that given a low resolution pixel, you have many plausible high resolution pixels in your target. And it is difficult to generalize, and therefore it leads to like very poor structural recovery and also fail to recover faithful textures. And people still want to solve this problem because it has many applications, like for example, to enhance the images obtained from satellite imaging for the purpose of video surveillance, for medical imaging, and also turning low resolution movies or films into high definition resources, and also perform like digital image enhancement. So over the last few years, my team has been focusing on the topic on image and video super resolution. So it's an interesting and exciting topic. We started this topic back in 2014. We proposed the first convolutional neural network for super resolution in ECCV 2014, which is the top conference in our field. And then after that, we have been improving our methods and extending it to different applications such as depth map, super resolution, and also face hallucination. And later, we also extended our work to video super resolution. Notable methods include UDSR and also basic VSR. With this method, we won multiple champions in the entire challenge, which is an important challenge for image and video restoration. And one of the important directions in super resolution is to improve the texture quality of the generated images. The texture has to be faithful to the original semantics, and yet it has to be photorealistic. And 3 years ago, we proposed ESRGAN, an improved version of SRGAN proposed by Twitter. So it generates detailed texture thanks to the improved adversarial loss, and it soon becomes an important tool for game modders to remaster various classic games such as Resident Evil and Doom. And in 2020, we proposed a deep generative prior, which is a model that uses GAN inversion as a way to enhance the details of a downsample image, and it's purely unsupervised. And this year we proposed, basically last year we proposed Gleam, a better way to perform large-scale super resolution with photorealistic details. So here I show some examples obtained by our method Gleam. Given a low resolution input as with pixels of like 87 times 87 pixels, we can upscale the image to high definition ones, recovering all the details like hairs and facial hairs. This is another example. And despite the heavily compressed image and noises, our method can reveal the details after super resolution. And this is impossible in the past. And this is another example. Our method can also be used to for old photo restoration. So this is simply an image that we obtain from the internet. And we can perform a very good super resolution. You can see the details recover. We can even recover the details of the eyebrows and eye lashes. Okay, so those are the examples on super resolution. It's part of the content enhancement research that we have been doing. So another topic that we have been doing is video super resolution. So this is a harder topic in the sense that you need to combine information from multiple frames to get the high quality output. So when you align multiple frames together, it's always difficult because the objects are moving and then the camera is moving as well. So you always have some misalignment. And we always need a better way to address this misalignment problem. So in our basic VSR series, we develop a new ways to propagate features or information for other frames effectively and combine them together to reconstruct the final output. And with this method, we won the very important challenge, also from the entire in 2021. So we got the first place, and we basically won other labs like from YouTube, Tencent, and Huawei, Baidu. So and many other winning solutions in other places. They basically use our earlier version of basic VSR or our last year winning solution, EDVR. So here I show an example. So at the left-hand side is the low resolution video input. And at the right-hand side is the output from our proposed basic VSR++. So you can see that despite the heavily compressed videos, our model can still recover the details. You can even restore the plate numbers. Okay, that's what we have been doing in image and video super resolution. Here, I just show a few examples of our method. So next, I move to content creation and editing. So we have been doing many work on image and video generation. So the core algorithm is still beyond GAN, but we improve the model by proposing better losses and better mechanisms to learn from those enabled data. So this shows our recent results published in NIRPS 2021. So basically, we can generate a very good looking phases that it's very hard to distinguish whether it's fake or real. And the advantage of our method is that it doesn't require many images to train the model. Compared to the original GAN model, which requires tens of thousands of images for training, our method require 10 times fewer images to train our model. That also causes shorter time in training and fewer resources. And we yet can generate very good looking images like this. And this is another effort of content editing and creation. So here I show some algorithms developed on face editing, which is very useful for creative content creation in film industry. So in the past, people need to do this using computer graphics. If you want to add age or you want to add a smile on faces. So here we show the possibility of doing it purely using deep learning methods. So given an image, our algorithm can change the different attributes of the person. For instance, changing the age of the person, or adding a smile to the face, adding a beard to the face, or adding hair. So the results are of high quality and it's easy to use without any need of computer graphics tools. So this is another interesting method that we have developed, which is again useful for creative content creation. So given an input image like this and any style image that you desire, then we can turn this input image to have a similar style of the chosen style image. So you can see the result is very good and is of high quality. So this is the first method that can cope with many different styles in a single deep neural network, and yet produces high quality and high resolution output. So it works well with like cartoon styles, those from pizza, and also caricature this, as well as Japanese anime. So here we show more examples turning a content like this based on a given style. Okay, for this example, what we did is that besides editing the attributes of the face by getting the users to interact with the software, we can actually manipulate the face, for example, how they talk, by using a source audio. So this will be useful for like dubbing for in film industry, where you always want to have a very synchronized lips movement based on a given source audio. So here I show how we can, the examples or the results that we can get by just simply inputting a source audio and generate a realistic video. Hope you can hear the audio.
We cannot hear the audio. We
cannot hear the audio. No. Okay, I don't know what happened. Basically, given the audio, yeah, the phases basically follows the audio and speak okay. The same sentence.
I think this is a conference system issue. So please go ahead.
Okay. And never mind, it's okay. It's okay if you can't hear the audio. I will just explain. Then in this example, basically we show that with the same audio, we can actually drive the lips motions of different phases from different angles. And all the lips regions here are generated purely by deep learning method. And we can also like change the words being spoken by the person. For example, if she is speaking this sentence, we can actually change the word. Now this is the original lip motion. We can remove these words and then we just let the lady to say knowledge is virtual, and we can manipulate the lip motion successfully. Okay, here basically is bad that you can't hear the audio. So what she's doing is to sing a song, and this song audio is actually cut from another person. Okay, from another person, and we manipulate the lip motion of this lady. Okay, and this is another example whereby we further add emotion to the manipulation. So this guy will speak the same sentence, but we can actually introduce an additional condition in terms of expression, whether you should speak it in an angry mood or a contempt mood or fear, with fear feeling. Yeah, this is the whole phases area over here is basically generated by the model. Yeah, so we can now edit the human face by audio and also by expression defined by a user. Okay, apart from like facial expression and facial components, we can also drive a human to make some post that is defined by another video. For instance, here we give a source video like this, then we will extract the skeleton, then we will retarget the motion, the pose, and also for example, the dancing movement to the targeted skeleton, and then retarget to the video. So this is useful when we want to drive, for example, avatar, or we want to drive a virtual human. So all this contributes to a new era of content creation. Okay, here I show how we can perform better 3D reconstruction. So this is also an important component of content creation, for example, in game industry. In our work, we just need a single image like this, then we can reconstruct the full high quality 3D human model like this. And with the 3D structure, we can relight it based on different lighting scenario. For example, if you are indoor, if you are outdoor, then we can relight the 3D model based on the environment. And what needs in the training is just single post human videos with unknown lighting and training. Yeah, and this is the latest work by our team. This is the first method that reconstruct garment from 3D point cloud and at the same time simulate realistic garment dynamics. So again, this is useful for game industry. And this is our old work published a few years back, but I still found it very interesting. Basically, given an original image like this, then you can extract all the objects from this single image, and then you can do manipulations in terms of order and positions and recompose a new image. We call this since the occlusion. And lastly, I show a video where we can perform a video embedding. We can use our algorithm to remove objects of any sizes. Then in the new video, you would just our method would just fill in the missing details and pixels. Okay, basically I show some examples of methods developed in our team. So just want to show that synthetic media is inevitable. So we are about to see a major paradigm shift in media creation and manipulation. And it's likely to change the entire industry in content creation. So synthetic media will significantly change or accelerate the creative expression and lessen the gap between idea and content. So in very near future, we'll be able to see more and more platforms that allow ordinary public to create interesting and very professional content using the platform. And it will bring new methods of communication and storytelling Yeah, basically enabling very exciting human-computer interfaces and challenge our perception of where the digital realm begins and ends. So that's good and bad. The ability to generate Hollywood-grade or better visual effects without the budget, time, and skill traditionally required opens up the potential for many applications. It can be good and bad. So while maximizing human creativity, we should also minimize the harmful use of AI. And our team has been working on that to develop tools that can automatically contextualize or detect the provenance of the media. Okay, that's all from my talk. Thank you.
Thanks, Professor Lloyd. It's great presentation to introduce your latest job in the deep learning. Thank you very much.